We've been learning about how to change bases, how to represent operators in different bases, how to go back and forth between them. We learned the importance of unitary transformations. The next thing that we need to know is the idea of something called a trace. Might have come across this before, but nevertheless I'll give you a quick reminder. This is essentially the trace of any operator is defined as the sum of its diagonal matrix elements computed in some basis. Okay, so I've chosen some basis. So then, what do I mean by the diagonal matrix elements? Look, I've sandwiched the operator x between the ket A and the bra A, and I've summed over all possible such cases. Okay, so these are called the diagonal matrix elements. Alright. If I wanted the off-diagonal matrix elements, then the ket and the bra would not necessarily have been the same. Alright. So the trace is always defined as the sum of all the diagonal matrix elements. Now, why bother? Okay, there are a couple of reasons why we bother. The first is that this object, this trace, whatever it is, it's actually invariant under the transformations that we were discussing in the last class, these generalized rotations. Okay. To see that, let's start from the trace computed in some basis A, which I have defined above. Okay. Now, I want to go to some new basis, B, which is defined in terms of U theta acting on the states A. Okay. So, in terms of these states, how would things look? Now, the way I'd figure that out is that I would be smart and say, look, out here in these two places, in between the ket and the operator, and between the bra and the operator, I can introduce a complete set of states, B, these rotated guys. Okay, that's what I do. But I have to be careful. I shouldn't introduce the same symbol B on both sides. I should do B and B prime. Does anyone know why? Why am I careful to keep things B and B prime? Because it would be somewhat misleading to keep it both of them. There is a reason for this. This is actually dummy variable. Why? What do I mean by dummy variable? Look, I'm summing over B. Alright. It's a complete set of states that I've introduced in the identity. And I have to sum over all of them. Okay? Now in general, when I introduce two such sets, there is no guarantee that I'm always going to get diagonal matrix elements. Okay? But if I were to say B on both sides, then I would sort of mistakenly have that impression that I'm always going to pick up diagonal guys. That's not true. In general, I will have all possible combinations that can appear. Which is why being explicit, just throw the door behind you. That's why being explicit and writing B as well as B prime is important. Now when you're solving an assignment problem, and if this kind of step is necessary, please bear this in mind. When you do introduce such dummy variables and you sum over them, there is no guarantee that you always have to return the same index. In general, you don't. You are going to sum over them. Right? So having taken care of that, you now have sums over both B and B prime, and we've introduced these projection operators, okay, which is what we should do. But now look what we've ended up with. We've got this matrix element here, which in general is an off-diagonal matrix element. It could be diagonal if B prime ket is equal to B bra, right? But it doesn't have to be. So that matrix elements I bring down here. And then I have two sets of inner products. Bra A with ket B and bra B prime with ket A, okay? Now, having got this, okay, I can do something smart. Which is, look at the curious way in which I've written this. I've actually got the ket here, right? The ket here and the bra here. So I've written it as a projection operator, and I actually have a sum over A. So I can actually replace this with the identity. I have the choice to do this, and I do it. Okay? So I end up with something simpler. All right? I have the matrix element here, and then what I ended up through this contraction was the inner product between B prime and ket B. But again, look, a miracle has happened. I've ended up with a projection between ket B and bra B, and I'm summing over B. So again, I can replace this with the identity, which I do, and look what I've ended up with. This time, no miracles, I've ended up with diagonal matrix elements. Ket B prime, bra B prime. Okay? And sum over all B prime. But that guy is the trace over this guy. Now, there was just one step. So given that this is a dummy index, instead of summing over B prime, I can call it B. God help me, I can call it anything I want. Who cares? So I decide to call it B. Then I trace over, and I say that look, this is the trace over that. So look where we started from. We started with tracing over A, and we ended up with the trace over B, the rotated guys. And what we just had established is that the trace doesn't change. And that was the statement that I started from. So this trace, whatever it is, the sum of all the diagonal guys, that's something that doesn't change. What does this mean, by the way? Think physically. What does this mean on physical grounds? When we say that the trace of some operator in some basis doesn't change, what does it mean? Take some simple example. Let's assume that this basis in which we took these matrix elements are its own eigenbasis. Then what will it correspond to? Let's take the momentum operator, and let's take the momentum basis. Then what would that trace correspond to? The sum of all the eigenvalues of the momentum. Okay? We call that the eigenspectrum. Here we've chosen the sum. Okay? So the sum of that entire eigenspectrum is something that doesn't change. And that's what I'm guaranteeing to you. Even if I rotate that eigenbasis into something else, the total sum of that eigenspectrum is guaranteed to remain invariant under that transformation. Please note this language. I used a very specific set of terms. I said invariant under the transformation. Invariant means did not change. Okay? It's not unvariant, it's invariant. And under the transformation. I carried out the transformation, this object remained the same. Okay? So I want you to take note of this phrase because that's again a phrase that we will often use. Okay? So I want you to understand what it means. Good. So now, having seen this, we can also note that if I take an operator which is dependent on some variable, lambda, okay, and if I carry out such a transformation on it, which means that I multiply it by some unitary operator on the right and its adjoint on the left, okay, and if this operator u theta can be written as e to the minus I lambda theta, okay, and so obviously u dagger is e to the I lambda theta. This rotation, if I carry this out, then it can be shown, and this is an important statement, it can be shown that if I take the derivative of this operator, lambda, with respect to this parameter lambda, then that's exactly equivalent to the commutator of theta, the generator of the transformations, with this operator a lambda, up to a factor of I. Now that's an exact statement. Okay, and we'll see consequences of this going forward. We will often use this. Yes?
You said that if we are thinking of it as an eigenbasis,
Mm-hmm.
then it's an eigenspectrum.
That's the understanding.
Let's say B is not the eigenbasis.
Yes.
Right. Then
Hey, Bishop. That has to be the most interesting excuse I've heard.
I mean, it is.
Last time I excused this. Make sure you don't come up with such interesting excuses next time. Even the call of nature may not save you. Yes.
You said that if A is the eigenbasis,
Yes.
then you get the eigenbasis.
Right.
Let's say B is not the eigenbasis.
Right.
So what is that physically means? You have that.
It means that you're taking again a trace over all the diagonal elements in that basis. So those are expectation values now. Those are not eigenvalues. But having said that, the sum of all the expectation values is conserved. It's equal to the sum of all the eigenvalues. Yes.
So last year we were changing the basis.
Yes.
So that B on B get is the same eigenvalue. Can we say that along with the sum the individual eigenvalue also not change when we are using it?
Yes, if that is true, if the indeed that's what we saw here. That's what you're reminding me of. Right? So those individual eigenvalues are indeed not changing. Right?
So like when we are
So that is the secret behind this trace. Because if those eigenvalues are not changing, then the sum also won't change. Right? Well spotted. Alright. Any other questions? Okay. Then let's see where this equation comes from. I want you to think about this for a moment. What is it telling us? It's telling us that if I carry out a rotation by some parameter lambda on some operator, right? So I have these unitary transformations, u of theta. Theta is the generator, lambda is the amount by which I carry out the transformation, the rotation. Okay? Then, how much does this operator change? That's the left-hand side. The derivative, right? It's keeping track of how much the operator has changed. And I'm making an exact statement. I'm saying it can only change as much as the commutator will allow. The commutator between which two operators? The object that was carrying out the transformation, the generator of the transformation is theta, and this operator. Okay? Sounds reasonable, okay, but it's an exact statement, so this must be quite powerful. And indeed, we will see how powerful this can get. But first, let's see where this statement actually comes from. Yeah.
Sir, the equation that A will be equal to U dash and A U.
Yes.
Would that not only hold if it already commutes with if A already commutes with
If
A commutes with B?
no, that's not true. That's not true. In general, it's not true. Because if that were true, then everything will simplify. All these nested commutators will all vanish. That's not guaranteed to be the case. So this, what I'm going to show you now, is an exact statement which doesn't need the commutator to vanish. So let me go through it and then we'll see. Alright? Okay. So let's start from the left-hand side. We're going to take this derivative. But that's a derivative of this object, where I've actually rotated the operator. And I've written it out explicitly. I've got those factors of e to the I lambda theta, e to the minus I lambda theta on both sides and the operator in the middle. Now, if you didn't know Baker-Campbell-Hausdorff, you would probably be having a heart attack right now, saying, how the hell should I carry this out? Okay, in principle, this would be nightmarish. Okay. Well, Baker-Campbell-Hausdorff actually helps us here, because we know that we can write down this awful looking expression, these two exponentials on these two sides with the operator in the middle. You can write it down in this expanded form. You might say, well, you know, this expanded form itself is horrible because it has an infinite order of, of these commutators, and they're all nested. Yes, but we will still find that it can get simplified. So I've taken this entire ugly expression in here, okay, and I'm going to carry out the derivative with respect to lambda. Now there we get lucky. Look, the first term won't appear. The first term isn't even dependent on lambda. Right? The second term is, so it just gives me this term. Right? The second term just gives me this. The third term, yes, it has this I lambda square, and that goes over into this, and so on and so forth. Right? Now look very carefully at what you're ending up with. If you look at that sequence, you'll see that the first term is this I commutator theta with A, that's this term. The next term is I times I lambda, and then it's a nested commutator, theta with theta of k. And then the third term is I again times I lambda whole square by 2 factorial, and then there are two nested commutators with that same object, commutator theta with k. So then there's something funny going on here. It's almost as if what we had earlier as the operator A has now become this commutator of theta with k. And we're just repeating the same game up to a factor of I sitting outside. Because if I take this I common, okay, then you can write this entire sequence as just the commutator of theta with this entire brutal expression. So the shift, so this derivative, what did it cause? It caused a shift, okay, essentially. Because the first term disappeared, and it appears that the second term took the place of the first, the third term took the place of the second, and so on and so forth. Okay, up to this factor of I, but it's again a commutator with theta. So that's quite nice. Okay. So earlier on, okay, we had that entire expression, and now it's appeared in a commutator with theta. And you can sum this entire expression and just write it as operator A of lambda. So all I did was I first unpacked that rotation. I wrote that e to the I lambda theta operator A, e to the minus I lambda theta. I wrote it as that brutal expression using Baker-Campbell-Hausdorff, and I carry out the differentiation faithfully, step by step. Okay, and then I note that look, wait, it's funny because now I'm starting with the commutator. Earlier on, I was starting with just the operator A, but now I'm starting with a commutator and a factor of I. So why don't I take that factor of I common and imagine that this entire expression is just a commutator with what? Theta with something. Because if you think about it, the first term is just theta with A. The second term is theta with this commutator. The next one is theta with this object, this commutator with theta of A, and so on and so forth. So then I just rewrite this in this language, and out drops this beautiful looking expression. It's very compact. So what is this telling us? It's telling us that we don't really need to do the entire Baker-Campbell-Hausdorff sequence in order to understand how that operator, how much that operator has changed by. We just take single commutator calculation and we know the entire answer. Okay? That's the power of what we've achieved. A beautiful example of this is actually the time evolution, for any operator. So consider some time evolved operator A as a function of t. I could have started, let's say, with that operator time t equals to 0. And then I could have time evolved it. How would I have time evolved it? Well, I know these unitary time evolution operators, e to the minus ith, the Hamiltonian by h bar. And I sandwich that on the two sides. This is how you carry out the time evolution. You take the operator and push the time evolution operator and its Hermitian conjugate on the two sides. That is the generalized time rotation. Okay. It evolves this operator forward in time. When you do that, this is the object that you're playing with. That is the new operator, A as a function of t. So how much has this changed by? Well, if you carry out the maths, you can see that what you end up with, if you just carry out this expression, you see that you receive something like this. IH bar times the time derivative of this operator is just the commutator of that operator with the Hamiltonian. And I don't know whether, how many of you actually saw this in the first course in quantum mechanics? Did any of you see it in your first course? Alright, then we will see a lot of it going forward. This is the so-called time evolution operation. And when you think about it, this is one of the things that we're always interested in. Anything you measure in the laboratory is always going to change with time. It's going to evolve with time. And here's a very simple recipe by which you can make predictions. Suppose somebody asks you, okay, I have this complicated system, I want to know how its momentum changes in time. Right? And you say, okay, yeah.
Should it be, given the above formula, should it be H commutator 80? Written 80 commutator H.
Let's see what I did there.
Minus I.
Okay, it was 1 by IH.
If I made a mistake, we can discuss this after class. Alright? But what are we saying there? What we're saying is that I can then step forward and say, okay, you wanted to know how the momentum changes. I can at least tell you how the operator changes very easily. And then if you want, I can give you numbers as well. How would you know how the operator changes? You say, okay, give me the Hamiltonian for the system. Once you got the Hamiltonian for the system, you just compute the commutator and that's it. You know how the operator evolved. Then of course you can take this object and then you can compute things with it. Sandwich it in between the eigenstates. If you happen to know the eigenstates, you get the exact experimental values. Right? You can compare with what was found by the the experimentalists. You can do that. This is an extremely important statement that's being made, and it's very compact.
Sir?
Yeah.
So in the Schrodinger equation, isn't the Hamiltonian itself written as analytical?
Sorry,
In the Schrodinger equation, isn't the Hamiltonian itself written as analytical?
yes, it is. Sorry, is it not the? Why don't I write this object as H itself? H acting on A. We'll see that going forward. Okay, I won't answer that question right now. But this equation has a name. And just like in your first course, you were following the Schrodinger way of doing things. This goes by the name of Heisenberg. Heisenberg was the one who actually set up this way of looking at things. And it turns out that these two are compatible ways of doing quantum mechanics. Does anyone know the difference between these two? These two ways of doing quantum mechanics? Yeah.
So, in the Schrodinger picture, the gets evolved. The operators are static.
Right.
In the Heisenberg picture, the gets are static, so the operators are
Right. So let me repeat that in case you missed it. In Schrodinger's way of doing things, we allow the states, which could be represented by some gets or some wave functions, whatever. We allow those to evolve. But we allow the operators, we don't allow them to evolve in time. We keep them static, we keep them fixed in time. Think back to your hydrogen Hamiltonian or your momentum in the particle in a box or any such operator from your first course. They never changed in time. Right? But the states always did. Now you might wonder, is that the only way to do things? Turns out that Werner Heisenberg came up with a different way of doing things. And he said, look, I can also have it the other way around. I can have the states fixed in time, but I can allow the operators to evolve in time. Okay? Maybe that was the reason why none of you saw this picture in the first course. Turns out that it's usually in the second course in quantum mechanics that we show you both these pictures. And indeed, there's a third picture as well. It's called the interaction picture. And I will briefly discuss that as well. Right. So this is the Heisenberg equation of motion for the operator A of t. And typically, you will never see this in the first course. The operators in the Schrodinger picture never evolve. So that's why you would never have seen it. It's just that simple. Before we wind up this discussion, let me just briefly mention how things would look like if you really put them into the matrix picture. Now, the matrix representation of some operator in some basis A. Srivasa, something amusing you? Share the joke. Must be something very funny or very mathematical. Feel free to share.
I said it took me 1 month to understand this. That's all.
I'm sorry?
I said to him it took me 1 month to understand this.
1
month.
Oh, it takes you 1 month to understand. Okay. Let's see if you can speed this up. Now, having gone through all the hard work of trying to understand how to transform an operator from one basis to another, let's just do something very simple. Let's just write the operator x in some basis A. And we know how to do this. Okay? All I've done, like I've done in the past as well, is that I took two of these identities, put them on both sides of the operator. I've ended up with a matrix element. Okay? And in general, I've got this object, this bra on one side and the ket on the other side. Okay? And I have to sum over all these states. Note, I've not written them as sum over A, sum over A. In general, it's sum over A prime and sum over A. Okay? Now these matrix elements, this is the way in which we could write down this operator in terms of these matrix elements. We can denote this entire object, okay, as all these fellows, right, written in the form of this general, I don't know, countably infinite times countably infinite in size matrix. And these guys sitting on the side, this bra and this ket, one of these, this will become like a column vector. This would become like a row vector, if you wish. Alright? And this object out here is this matrix representation that I'm thinking about. Now, if I have the eigenstate representation, now this, of course, was brutal if it's in any basis. But if it happens to be the eigenbasis of this operator, then actually things begin to look even simpler in the matrix representation. Why? Because in general, if you have this huge matrix in front of you, what are you going to do with it? It could potentially have how many terms? Infinity squared. Because you're going to have countably infinite in one way along the rows, and countably infinite along the columns as well. So this is horrible. And yet, if you're smart, you recognize, wait, I can make this look a little simpler. And the way you do it is you go to the eigenbasis. You go to the eigenbasis, okay, in that case, things begin to look simple. Why? Because now these matrix elements become extremely simple. Because X operator acting on get X just pulls out, sorry, this thing shouldn't have been there, that's a typo. This pulls out the eigenvalue, X, and multiplied by a Kronecker delta. Alright? Now this entire matrix element now simplifies. It just becomes this object, okay, a number, the eigenvalue, and the Kronecker delta. This Kronecker delta imposes the fact that one of the sums you don't need to do. Why? Because it says that the ket and the bra must be identical to one another for this object to be meaningful. Right? So in that case, you're just left with these eigenvalues times this object, these projection operators. So this is a very simplified way in which we could write it. So the matrix representation will just look like x1 times x1, x1, and then 0, 0, 0 all the way. And then the next term would be 0, and then you'd have x2, 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 and then 0, 0 all the way. And so on and so forth. So you can see that you will only get new terms appearing along the diagonals. Okay? Everything else is a 0. So this is why we call the eigenstate basis, right? That this basis in which everything becomes diagonal. You're just picking out the eigenvalues. This makes sense. Life should become simple in the eigenbasis. If you're not in the eigenbasis, things will look hideously complicated. So this is common sense. Look for the eigenbasis of that operator, and then the eigenvalues are just sitting on the diagonals, multiplied by the projection operators. Why do we need the projection operators? Why couldn't we just have had a matrix of just diagonal numbers? Why do we need the projection operators? Because you have an operator on the left-hand side, guys. If you just had numbers appearing on the diagonal, then that's a matrix of numbers. What has this got to do with quantum mechanics? If you want an operator on the left-hand side, then those numbers have to be multiplying some operators. And which operators? Well, these are the operators that project you onto each and every member of the eigenbasis. The x1 projection operator projects you onto the first eigenstate, the x2 projection operator onto the second eigenstate, so on and so forth. This is obvious. Right?
So is this general for any other?
This is very general.
It is multiply with projection.
Absolutely. So any operator, if it's written in its own eigenbasis, will just be the eigenvalues multiplied by the projection operators made out of the eigenstates. Powerful, isn't it?
So how do we play around with this?
What do you mean, how do you play around? What do you want to do with it? Yeah, you can get the trace from it, but you can do much more, right? Because now you can pick out each and every one of the eigenvalues as well if you know the eigenstates. You just project onto one of those eigenstates and bang, you get one eigenvalue. Right? You still have to solve the eigenvalue problem, obviously. I mean, life's not going to come for free, right? If life was that simple, then there's nothing left to do. So you always have to, I mean, having said this, you also have to solve the eigenvalue problem. This is just telling you that once you solve it, once you know those eigenstates and their eigenvalues, everything is done. This representation is complete. It's perfect. The one that we're really looking for in quantum mechanics all the time is this object, this diagonal representation, but for the Hamiltonian. Anytime you are playing with a quantum world, the first operator that you really want to know in its diagonal basis is that of the Hamiltonian, the energy basis. Okay? So if the Hamiltonian acts on some state psi, right? And if the state psi belongs to its eigenbasis, then we can always write it in this way. We have the energy eigenvalues acting on the projection operators. Okay. Now, when you act with this bra on this ket, okay, it's just going to pull out a delta, a Kronecker delta. And as soon as you've imposed that Kronecker delta, it gives you the particular eigenvalue. So this, if you wish, is the projection where we use this particular inner product to get out this Kronecker delta. This Kronecker delta simplified the sum and took one particular eigenvalue. So this is a mathematical way by which physicists understand the mysterious collapse of the wave function. Okay? In general, let's say, you had a more general state and you picked out one of them, it would look like this. We got lucky here because we were working in the eigenstate basis itself, and it was very simple for that operator to just pick out this guy. But what does picking it out mean? In general, you're going to always fall back on some particular inner product. That inner product is going to choose the state into which you will collapse. Okay? Experimentally, we don't understand how this happens, but we have a mathematical recipe for it. Let me call it a recipe. Okay? Yeah.
You have the Hamiltonian.
Yeah.
Each I prime and out.
Oh, in general, it doesn't have to be the same as state psi. It's a dummy index. I can keep it anything. I could have called it.
You should put an E.
Oh, that's the energy eigenvalues. What are these guys? These are the energy eigenvalues. These E reflect the energy eigenvalues. All the possible energy eigenvalues. And this is the one, this final one, this is the one you picked out.
Okay.
So I've just used the representation above, and I've just used the Hamiltonian in its energy eigenbasis. So this is a whole lot of maths that we've had to set up in order to be comfortable with this notation of kets and bras, how to get out eigenvalues, how to get out matrix elements, expectation values, etc., etc. Rotations. We've looked at a whole variety of concepts. Now, let's look at another consequence of all of this. And it goes by the name of the uncertainty principle. This is something that you were exposed to in the first course, but you need to understand it a little better now. what this really means. Okay. So roughly 100 years ago, perhaps somewhere close to this peak point in time, is where Werner Heisenberg decided to take a holiday, left Göttingen, and went off to the North Sea, because the claim was that he was unwell, he was suffering with hay fever. It could also be that he was just sick and tired of hanging around in Göttingen, and he needed to take a break. That happens. And he went to an island in the North Sea, and it was during his sojourn there that the final pieces of the clue, that he was working on, led to what we're going to see now, this so-called uncertainty principle. So it's not clear that he actually solved everything while he was on that holiday, but it's certainly true that it was there that he finally had that epiphanic moment where he realized, okay, now it all makes sense. Right? Which is why very recently, I don't know whether you're aware, but maybe roughly about 2-3 weeks ago, on that island in the North Sea, the Europeans actually celebrated 100 years of the uncertainty principle. Go look it up. It was quite a big event. Where, the EU spent a lot of money bringing a lot of people together to just celebrate that moment. Let's study what this looks like. Okay? So, first of all, if Heisenberg had been a student of mathematics, then he would not have been surprised at what he was looking for. This object, to any student of maths and statistics, is reasonably familiar, even in his time. Okay? This object is called the standard deviation. Alright? And what is it? It basically says that, look, let's not think about operators acting on states or whatever. Let's imagine this is some object, okay, that you're picking out from an ensemble. You have a large distribution of that object, and you're just picking it out randomly, okay, over a certain number of trials, and then you want to get out what is the average, and you want to know what is the so-called standard deviation in that quantity. Now it turns out that this object, this way of writing things, that's the average that you get out for that quantity. And what is the standard deviation? It's where you take that quantity, subtract it from its average. So every such trial that you took, okay, so imagine, let's say, okay, so let's take a concrete example. Your friend is throwing a ball across to another friend. And let's say you repeat this experiment 1,000,000 times. Yeah, your two friends are going to get bored, but let's say we want to recreate this. So let's say that same act of throwing the ball happens. And you want to measure how long it took for the ball to reach your other friend. And you keep measuring this. And you do this over 1,000,000 such trials. Okay. So you can compute the average from this. You all know how to do that. But this standard deviation would mean that you take each and every instance of this, this time measurement. You subtract the average time from it. You square that. You sum over all of them, and then you take the square root. Okay? That's what the standard deviation corresponds to. Now, in terms of a statistical distribution, what it would mean was that if you have all the trials noted down here, okay, so these are the values of that quantity, and these are all the trials noted here. The first time you did it, the second time, etc. Okay, then this, typically the mean is somewhere near the peak of this. We don't have to worry about the fact that it could be a unimodal distribution, it could be bimodal. I've just given you something to represent this. So imagine that this peak represents the mean. Then, in that case, the standard deviation would correspond to the width of the peak. Okay. Which width? Does anyone know which width?
Full width half.
Full width half maximum. So can anyone tell me what this full width half maximum means?
So when you at the value where it
Okay, so let's take that value at which it was there. Then we note when it comes down to half that value, right? And that's where we compute the width. Okay, so that thing is what we call the standard deviation. So what does this mean? What does it mean on physical grounds?
the spread in the value.
The spread in the value. But what does the spread mean? How much what deviates from the mean? So in this experiment, you were measuring, how much time the ball took to go. Sorry, again we're using words like expectation value. I don't know what that means. We have a set of values that we got.
And how much all the values did.
Typically, how far would they be away from the average? That's what this would be. So it's like a typical value. Okay. That's what it means. So I carried out this experiment 1,000,000 times. Typically, how far would I be from the average? That's what this would be. And if this thing is extremely broad, what does that mean? It means that your friend who's throwing the ball is a lousy thrower. God damn it, over 1,000,000 tries, this friend of yours has been taking very, very different times. If this guy was really good, then how would this distribution look? A sharp delta function. So if your friend was a cricket player playing for the Indian cricket team, you would expect this standard deviation to be what? Very broad or very sharp? Very sharp, otherwise they won't get in there. But if it's you out there, even if you're playing for ISA Kolkata's cricket team, I would reasonably expect this thing to be broad. Okay? Because you're spending more time in my bloody classroom than on that cricket field. That's the obvious reason. Okay. So now let's take this into the world of quantum mechanics. So we know how to take expectation. Now let's get to expectation values, like this. Okay. We know how to compute these expectation values. I've chosen the real space representation, wave functions written in real space. Okay. So that's the thing for x. For the linear momentum p of x, I sandwich it in the middle. You know how to do this. Okay. So for the sake of brevity, henceforth, if I'm cavalier and I drop these hats, please understand that I'm talking about the operators. Okay? You should know from the context when I'm talking about an operator and when I'm talking about an eigenvalue. Right? Learn to spot this, because always keeping a hat becomes very painful after a while. Okay. Now, we want to get the Heisenberg uncertainty principle, HUP. How do we do that? The way we do that is that we do something peculiar. I've considered this quantity. Instead of the expectation value, look at what I'm starting with on the left-hand side. That's really a peculiar beast. What have I done? I've taken the x operator and I've plugged it in between the psi and the psi star. So up to there, it would have looked like a matrix, it would have looked like an expectation value of x. But I've done something a little dirty as well. I've acted with something that looks like the momentum operator and made it act on this entire object. But is it exactly the momentum operator? No. Why is it not the momentum operator? What's missing from it? The minus sign. So can I bring back the minus sign somehow? If I were to take this object, this IH part delta x, and if I were to just place it inside here, then it would have looked like the momentum. Okay. But for the time being, let me just keep it the way it is. Alright? And let's go forward. So I've taken this dirty beast, whatever it is. Alright? Good. Now what do I do with this? Well, I can always do an integration by parts. If I do an integration by parts, alright, then I'm going to get a term that looks like this coming out. Okay. But that term will just pick up values where? At the boundaries. These are the boundary pieces of the integration by parts. And then I'll have something where I've ended up looking with something like this. Alright. But the first term, right? So, by the way, even in getting to here, I would have had to do another trick. I don't know whether any of you spotted it. How did I end up with something like this? I've had to throw away a fair few terms. Okay, I'll leave it to you to figure out. Go do this. Go calculate this integral and see it for yourself. But the claim is, that there's going to be a term of this kind that's going to appear. Okay? And I'm going to throw that away. Why am I going to throw that away? Because it's going to involve objects, wave functions at spatial infinity, plus minus infinity. And there, if these wave functions are square integrable, these wave functions should decay, go to 0. Otherwise, I don't even know what I'm doing. So this term is going to drop out. Okay. Now, I'm going to take the second term and rewrite it as a complex conjugate. But a complex conjugate of what? This fellow inside its complex conjugate. Okay. So this minus sign at that point became the plus, became this plus. Okay. So the minus H bar became a plus H bar, and it ended up with something that looks like this. Now look at this guy inside the box. Do you recognize it? The guy inside the box? Where have you seen it? It's this fellow. It's this fellow. The guy on the left. So this fellow that I've ended up inside this box is just the guy I started with. Okay. So what I've done is I started with that guy. I carried out some transformation, some integration by parts. You need to think carefully about how many times I would have had to do this. But finally, I've ended up with something that again looks like it, but up to a complex conjugation. Now ask yourself, since I'm carrying out such an integral, what could this have given me? Could this be an operator? Could this guy on the left hand side be an operator? It's an integral, right? Can this be an operator? What is it? It must be some number. It has to have some value. But does it have to be real? No. In general, it doesn't. In general, it must be complex. So which means that this object is some complex number C, and out here I've ended up with the complex conjugation of that same number. So I can take this across to the other side, right? C, and it becomes C minus C star. But if I have a C and I have it C star and I take the subtraction of the two, then I'm just picking out 2 times the imaginary value of that complex number, multiplied up to a factor of I. Okay? So then this right hand side, after I take this guy across to the other side, is just this guy. 2 times the imaginary and the imaginary value of that integral, whatever that object is. We'll see how to simplify that object. And on the right hand side, I have this. But the right hand side is actually also quite nice. Why is the right hand side, why is the left hand side nice? It's just the probability density. Okay, great. So then I just take the squares of both of these. I take this entire left hand side, right hand side object and I square. Take its second power. When I do that, that integral, that's just going to give me 1. Okay? Actually, it's not the square, I take the mod square. So this IH now becomes, I multiply by minus I times H bar. So it gives me H bar square. This object will become equal to 1. And here, whatever I have, since I take the mod square, this I factor will also disappear. I'll end up with a 4, and then I'll get the mod square of this integral. So whatever that beast is, it's some complex number, okay, coming out of the integral. I take its imaginary part, and I take its mod square, okay. So I've ended up with the fact that H bar square should be equal to 4 times this mod square. And it turns out that we're actually pretty close to the Heisenberg uncertainty principle. But to recognize that, you have to be a little smart. What you have to recognize is that the imaginary part of that integral within the mod square, it must be less than equal to that entire integral, if you think about it. The imaginary part must be less than equal to the full guy. Just take any complex number, a plus ib. The b part must be less than the norm, square root of a square plus b square. Just that simple. So therefore, I can always write that the middle term as being less than or equal to 4 times this integral, which is, I just dropped the imaginary part. Okay? I can do that, fine. Now, we can use the Schwarz inequality. We have this integral out here, okay? And we need to recognize that, wait, I have here 2 objects playing around. Remember, right in the beginning, we looked at this and said, yes, we have a position operator there, but we also have something that looks like a momentum operator. Okay? So the smart thing to do now is to realize that, yes, this object, okay, if I use the Schwarz inequality, I should be able to say that this object is less than or equal to this object times this value. What are these two? What are these two products? If you look carefully at it, it's actually the expectation value of the x square operator and the momentum square operator. Okay? So this object on the left hand side, this integral, whatever it is, has to be less than or equal to the product of the expectation value of the position square and the momentum square expectation value. These two products have to be greater than or equal to this guy. So I substitute that into the above. So 6.6 now simplifies, and I have the fact that h bar square by 4, so I've taken this 4 and I've taken it to the other side. This h bar square by 4 must be less than or equal to the product of the expectation value of x square and p square. Okay. That is the simplest form of the Heisenberg uncertainty principle that you can think of. Why do I call this the simplest form? You've probably seen this form. Something of this kind. Okay. But this guy is a yet simpler version of this. Why do I say that? Because if I take a square root on both sides, I have a square root of x square and I have a square root of p square. This guy is not the uncertainty, right, in general? What is delta p defined as?
It's mean of the square minus square of the under root.
Right? Now this will, when does this delta p become the one that I have just above it? When does this guy equal to this? When the mean is equal to 0.
So in the data is equal to square root. There will be one more expectation.
That's right, sorry, my bad. There's one more expectation. Thank you. So this term goes into the simple expectation of p square with a square root only when the average of p is 0. So what I showed you here is the simplest form of the Heisenberg uncertainty principle for the special case where the expectation value for both p and x are identically 0. But that doesn't have to be the case. Right? So this is one special case. For the more general case, note that if we were to replace everything that we've done above in terms of these quantities, instead of working with x and p in the above, if we had worked with the difference of x from its expectation value and the difference of t with its expectation value, then after all the maths, you would end up with precisely the Heisenberg uncertainty principle. Okay. So this derivation was a fair bit of maths. Let's just quickly look at it again. We started with some object which had a mixed nature. It had both x and t. What did we do? We carried out some integration by parts and rewrote it in such a way that the same object appears on the right hand side but in its complex conjugate. I take that across, okay, and write it as the imaginary part of that. I square, okay, I take the mod square of those, and then I use the fact that the mod square of the imaginary must be less than the mod square of the full guy, the full complex number. I then use the Schwarz inequality and replace this entire object as the product of x square and p square, expectation values. Alright? And then I find the simplest version of Heisenberg's uncertainty principle. To get the more general version, replace everything I did here with these quantities. The difference of the expectation values from the operators. Repeat the same program and you end up with Heisenberg's uncertainty principle. This is the form that we are most generally familiar with. Okay. Now everything that we did here was just kosher mathematics. I never needed to invoke any special features of any given quantum system in making these arguments. Okay. All of this comes out of the simple maths of the linear algebra or vector spaces. This is what it took a lot of people time to digest. That Heisenberg's uncertainty principle wasn't telling them about the physical limitations of some experimental apparatus that they were working with. It was a far more profound and fundamental truth about the quantum world. It just says that if you are working with a particular set of, let's say, eigenstates, here, let's choose the position eigenstates. If you choose the position eigenstates, then all the delta x's will just vanish. They will go to 0. Okay? But more shockingly, what it tells you is that in that basis, the uncertainty for your momentum observations, no matter how good an experimentalist you are or how good your apparatus is, those uncertainties are going to be huge, massive. Initially, people misunderstood this to be a statement that we just need to make better measurement devices and it should all improve. It was only somewhat later that people began to realize that no, this is just within the mathematical structure of the Hilbert space that we're playing with. Okay. One set of measurements, the precision in one set of measurements comes at the cost in the precision of a conjugate set of measurements. Now the real question, once you've taken this on board, the real question then is which operators obey such relations and why? Okay. So one example we've seen here was position and the momentum, the linear momentum associated with that position. Right? And you could say, okay, why those two? Why, suppose I took x with p of y, or with the Hamiltonian, x with the Hamiltonian. Would all of these work? Well, it turns out that this statement has even a more precise form. Let me just show you what that form looks like. And then we'll do it in the next class. It looks like this. The more precise form looks like this. If you take the product of the expectation value of two operators, okay, any two operators, A and B, then it's their commutator and its matrix element that's sitting on the right hand side. So what did we take up here? We had h bar by 2. You can easily convince yourself that if I had taken A and B to be x and p of x, what is the commutator of this? If I take the mod of that, what will happen to the I? It just disappears. And you'll end up with this, the Heisenberg uncertainty principle that we got. So what that is telling us is that it's not just any two operators that are going to give you this. There are certain classes of operators that actually lead to this. And those classes of operators have very non-trivial commutation relations between them. Okay? When that is satisfied, out pops this Heisenberg uncertainty principle. Okay? Those operators are called conjugate to one another. So we use a word, conjugate. We say that x and the linear momentum associated with x are conjugate to one another. That's when such an operator valued commutator holds. And that's when this Heisenberg uncertainty principle appears. Okay? So the Heisenberg uncertainty principle doesn't appear just when you feel like it. It appears at very special points. Alright, thank you.